Hello everyone, my name is Sheroz Khan. I'm a Marie Curie Fellow at the University of Strathclyde. Today I'm going to briefly talk about work on Bayesian shape optimization in high-dimensional design spaces using isogeometric boundary element analysis. This work is jointly carried out by the University of Strathclyde, Institute of Marine Engineering, and Nazarbayev University. So let me give you a brief overview of a typical shape optimization problem. So consider we have a design, in our case, a ship design, which is parameterized with three different parameters. So these three parameters will give us a three-dimensional design space where this sphere represents any design instance, a random design instance. With this, we have a shape modification method. So any design instance, for any parametric instance, the shape modification method will update the designs and will give us a new design. And we also have our performance evaluation code, which gives us the performance criteria we are interested in. Then we have an optimizer, with the help of which we're going to explore the design space to find an optimal design. So this process will continue, this loop will continue until we find an unoptimized design. But you can tell me, Sheroz, look, your design space is only three-dimensional, so most probably you won't be able to find a most optimized design. Okay, I will fully agree with you. I will say, okay, we can reparameterize our design with large number of parameters, so where we can have higher possibility to find the most optimal design. But this high number of parameters will give us a high dimensional design space, okay? With this high dimensional design space, the chances of falling or causing in this notorious curse of dimensionality, and it individually increase our computational cost, and this cost varies exponentially with the dimensionality of the design space. And this high computational cost is mostly centered towards the three component, mainly towards the performance managed code. We all know that CFD solvers are highly computationally demanding. This is also somewhat centered towards the shape modification method and optimizer. So the entire pipeline, the computational complexity of the entire pipeline increases exponentially. In literature, to tackle the previously mentioned problems, there are two mostly used approaches. One is dimension reduction to reduce the curse of dimensionality, and the another is surrogate modeling, where we can bypass the need of carrying this computationally expensive simulations for each of the design instant. But for reliable training of any of these approaches, we need big data sets. And these the need for the big data set is critical, especially for the high dimensional problems. So, and constructing this data set can be itself a computationally expensive code, because as I said, like each of our physical simulation is of high fidelity, and running a single simulation is very expensive. So the problem of using these approaches itself is a computationally expensive cost. So in this case, the problem of computational complexity still exists. So to tackle this problem, we connect dimension reduction, Bayesian optimization, and isogeometric analysis. So dimension reduction is to reduce the overall dimensionality of the design space, and Bayesian optimization is to avoid the need of preliminary running or creating a large amount of data set. And isogeometric analysis is for the robust design evaluation during the whole process. So here is the overall layout of our dimension reduction. Consider we have a parent design which is parameterized, and each design parameter is bounded by a parametric range. And this gives us a high dimensional design spaces. So we first sample this design space, and then for each the sample design from this design space, we discretize it. And with this, using this discretization, we implement our dimension reduction. In our case, the dimension reduction is implemented using Kern-Hanen love expansion, which I will explain in the coming slides. And once this dimension reduction is implemented, we get our lower dimensional subspace. Once we our lower dimensional subspace, we resample it and we reproject it to a high dimensional space. So, but at this reprojections, because we implemented our previously the dimension reduction on the discretization, so in our case we will get a discretized design. But for isogeometric analysis, we know that they are implemented directly on the nerve surface. So we construct from this discretization a nerve surface, but the nerve surface that we get is of high dimensional, high degrees of freedoms, which can significantly increase the computational cost during the analysis. So we simplify the design, by reducing or by eliminating the redundant degrees of freedom. And once we have this simplified design, we run over isogeometric analysis. With this one, we create over a small data set, which is initially used for running the Bayesian optimization. Consider we have a three-dimensional body, which is enclosed by a two-dimensional manifold G calligraphic. And this G calligraphic, which is our design ship in our case, is parameterized with n geometric parameters. And each parameter is represented as T. And then this T bold is a vector containing all the parameters. Because we have parameterized our manifold with n parameters, and this will create a n-dimensional design space, which is represented as T calligraphic. Then this design space is bounded by an upper and the lower bound. With this one, the T yields a continuous shape modification function, vector function, G, whose dimensionality is 3 because we are considering a three-dimensional design shape. So for any parametric instant, in this design space, we take that and then we add it with our shape modification function, and this gives us a modified design. So in terms of dimensionality reduction, our aim is to find a lower dimensional representation of our shape modification function. So instead of T, which is a large number of parameters, it depends on a lower subset of parameters. As I explained in the previous slide, the aim of the dimensionality reduction is to find a lower dimensional representation of this shape modification function, which previously depended on this parameter set T, and it's lower dimensional representation. It depends on V. So the V in our case now is a geometrically active feature set, and whose dimensionality is much lower than the original design, the design space. So how do we find this lower dimensional representation of the shape modification function? So we implement the KLE, Cantilever expansion, on the original shape modification function, whose aim is to find the optimum orthogonal basis, this omega, which approximates the original function. And the number of this, the bases to be used to extract the features, it depends on the optimal condition for KLE, which is we have to retain the maximum geometric variance which exists in the original design space. So once we find these features, now our shape modification function will have the reduced dimensionality, and it will create a reduced dimensional design space. To test the proposed approach, we used DTMB 5415 ship model, whose main particulars are given on the right in the table. And this design is parameterized with 27 different parameters. And this parameterization and the modification of this design is, as explained previously, depends on a global shape modification function. So I haven't given detail on this, the function, but you can find it in our paper. The aim of our optimization problem is to reduce the wave resistance of the ship model. So the wave resistance is amount of energy that is generated when a ship or hull move at the free surface of ocean, sea, river, or lake. So this wave resistance coefficient is a very computationally expensive criteria and widely used in for ship optimization, and it is very sensitive to the modification or changes to the local feature of the designs, especially at the bow. And it is very critical for us as naval architects to minimize this at the preliminary design stage. So first, to implement the dimensionality reduction, we sampled uniformly distributed designs from our original design space using Monte Carlo method, the design space which was 27-dimensional. Here you can see the design variations that we generated from our shape modification method or our parameterization using 27 parameters. And here are the results of the dimensional reduction. You can see that original design space is 27-dimensional and the reduced design space is 15-dimensional. And we have achieved a significant amount of reduction of 44% approximately, while retaining almost 95% of the geometric variance. And here you can see first three eigenvectors. With this one, you can see like most of the modifications in the design take place at the front and at the back end, which we call off part of the ship. So once we achieved our reduced 14-dimensional design space, we run Bayesian optimization with Gaussian processes regressions, and without going into the details, at the end of the optimizations, we achieved a significantly better performance. So from 0.8 achieve the reduction up to 3.8. So, and here you can see the difference between the optimized and the original designs. And over here, lines are just the orthogonal projections or the body planes of the shape on the orthogonal plane, just for the comparison.